All right, good day to you, students. We're continuing chapter 7 now, and actually, this should say 7.4. Not sure how that happened. But we are in section 7.4, and our whole chapter is about similarity. And this is going to be particularly similarity in um, right triangles. So there's some interesting relationships that we deal with. And the goal is I can find and use relationships in similar right triangles. So, I'm going to start off. Our essential understanding, something that you have to know, is when you draw the hypotenuse, so we'll say this, the altitude to the hypotenuse. Now remember, the hypotenuse is the longest side of a right triangle. So when you draw the altitude to the hypotenuse of a right triangle, you form three pairs of similar right triangles. So we have our theorem that we're going to base a lot of our stuff off of today. It says right here, the altitude of the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle. So when you make that altitude, you have the original big right triangle, and we have two smaller ones that are going to be similar to the larger one. So they're all similar. That means all the angles are going to be, corresponding angles are going to be the same, and they're all going to be proportional with the same scale factor. All right. So, a couple of examples just based off of that. First, it says identify the following in the right triangle to the right. The hypotenuse. All right, so the right hypotenuse of triangle XYZ would be XY, just so that we're getting a grasp as to what we're doing here. The segments of the hypotenuse. So when we're dealing with the segments of the hypotenuse, it's just breaking it up into two parts. So that would be XY or XR and RY. Those are important. We have two theorems that come off of that, corollaries that deal with those. The altitude to the hypotenuse. So you got to think back to, I think, chapter 5 was all about the special segments in triangles. One of them is the altitude, and that's the perpendicular line to one side, from one side to the opposite vertex. So the altitude to the hypotenuse, you have to be going to the hypotenuse and going to that opposite vertex, which would be right there. That'd be ZR or RZ. The segment of the hypotenuse adjacent to the leg ZY. Okay, so it's the segment of the hypotenuse that is adjacent to leg ZY. So it's the smaller one, so it's going to be RY. Alright, then write a similarity statement relating the three triangles. Alright, so we have this number 5 as a different set of triangles. We have triangle ABC as our first one. That is our largest one. Similar to that, we have to look at it. Now, in that one, B is our right angle. Alright, and it's hard to tell, but if you were to reorient that, I would maybe rotate it a little bit. We'd have BDC, I believe. Triangle BDC. And then similar to that would be triangle. That could be CDB. It's hard to tell right now. But let's look at a theorem. Let's see if we can tell. So triangle triangle ABC is similar to triangle ACD. All right, so the corresponding parts. So we're going to go with triangle ADB. Now this one's really hard to tell because we don't know which angles are bigger. It almost looks like they're 36 or 45, 45, 90 triangles. So we're going to go with that. All right. Now we're going to break this down a little bit. Actually, I have a couple examples first. So we've learned about proportions, and proportions in which the means are equal occur frequently. That means when we're dealing with the means and the extremes would be the top right and the bottom, or top left and the bottom right parts. So we're looking right here. This would be the extreme. So when the means are equal, those two other ones, that actually happens pretty commonly. For instance, 1 over 2 equals 2 over 4. The means are the same. So for any two positive numbers, a and b, the geometric mean of a and b is the positive number x, such that this would be a over x is 2x over b. So if we're looking at that, and if the means are congruent, if they're the same means, if they're equal, then you can say the geometric mean of a and b is x. So in this case, over to our right here, the geometric mean of 1 and 4 is 2. Alright? So use the algebra to find the geometric mean of each pair of numbers. So 4 over something is congruent to something over 9. So we just have to use algebra. So let's take that, solve our proportion. You'd have x squared, you do cross multiplication, x squared equals 36. So x equals, you take the square root of that, it could be 6 or negative 6. Alright? So the same thing with number 7 then. Why don't you try that one on your own? Alright, now it's, so 6 over x is equal to x over 12. So we'd have x times x is x squared. 6 times 12 is 72. Take the square root of that, both sides there, and we're going to say x is, I'm just going to leave it as plus or minus the square root of 72, because square root of 72 isn't going to work out perfectly, and it can be both positive or negative, so that's what we're going to leave it as. Alright, now we've got a nice little diagram here. In a pair of similar triangles, now we're going back to triangles, we can write a proportion with a geometric mean. So if we have triangle SQR or SQP is congruent to triangle SPR. So look at those SQP and SPR. We know that the short leg of the one triangle, the ratio of the short leg to the short leg of the other triangle is congruent to the long leg of that first one to the long leg of the other triangle. And that's just looking at corresponding parts, and if they're similar, that would make sense. But that is an example of a geometric um, mean, because the short leg of the one triangle is the same as the long leg of the other triangle. So these parts right here are actually the same thing. And that's how it's shown underneath there. Now, in section 1 we looked at proportion. Which diagonal is the means? Well, we talked about those middle ones, B and C. So if there's a problem that asks you to find the geometric mean between two numbers, you can put your variable on the means diagonal and your two numbers on the extremes. So that's what we kind of just did before using the algebra. Two important corollaries that we're going to talk about, and they're kind of, I have them shown in a couple different ways. The first one says, these are just from that theorem we just talked about before. First corollary to that theorem says the altitude is the geometric mean between segment 1 of the hypotenuse and segment 2 of the hypotenuse. So let's look at this down here. This is looking in a different way. The length of the altitude to the hypotenuse of the right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So if we look at a triangle, I like the example the best. Really what we're saying is the altitude to the hypotenuse of the big triangle, that's the 4 here, is a geometric mean. So you're setting it up, we have this proportion, that's going to be the one here and here. It's the geometric mean of the lengths of the segments of the hypotenuse, so the two smaller segments. So the smaller one, the 2 over 4, is going to be the geometric congruent to 4 over 8. And that makes sense. If you look at it, that makes sense for this example. If you look at the one without any words, if that, then we have that AD goes with CD, as CD goes with DB. The second one, depending on how you look at it, it's written right here for you. Yeah, and I don't know if I have them both ways in your notes, but the leg is the geometric mean between the entire hypotenuse and the segment of the hypotenuse closest to the leg. So we look at it like this, um, and I'll do this for corollary too. But the leg, so let's say we're doing AB. Actually, we should use the one over to the left. Let's do, of the whole thing, leg 1. Ugh. So the leg is the geometric mean. So leg 1 and leg 1 is the geometric mean of the entire hypotenuse and the one that's closest to that. So the entire hypotenuse would be h. So h is to leg 1 as side 1, or leg 1 is to side 1. So the one that's closest to it. So that would be one right here. Alright, and I have it a different way here. It says, it's a lot longer here, but if you look at the example, that's the most important part. Um, the whole entire hypotenuse for the whole triangle, the ratio of that to the one of the legs is equal to the ratio of that one leg to the smaller part of the hypotenuse on that triangle. So that would be this 1. So essentially you're looking at this. You're saying the hypotenuse of the big triangle to the one of the legs, so let's say in this case the smaller leg, is the same thing as the hypotenuse of this smaller triangle to the smaller leg of that. You're just doing corresponding parts. So don't overthink this. Don't be so confused about this. All you're doing is comparing right here. This would be the hypotenuses of the two triangles you're dealing with, and the bottom ones would be whatever leg. In this case, we're doing the smaller leg. If you're doing this larger leg, it'd have to be the larger leg for each of them. All right. So over here, if you fill this in, the first triangle we said was the um, altitude. So if we say the smaller segment, so let's say side 1 is to the altitude, which is A, is to the altitude as to goes to side 2. All right. Let's apply that a little bit now. So we look at number 8, and we're going to finish this up pretty quick. We have D is to C, so we're looking at the smaller one is to the altitude. So we have the altitude as the altitude is to E, we said. That's straight from that corollary. So this would be um, the one part of the hypotenuse goes to the altitude as the altitude goes to the other part of the hypotenuse. Number 9, and again, number 9 we're going to be dealing with the other one, I think. So if we're dealing with the whole hypotenuse of the whole big triangle, that's related to one leg. It doesn't matter which leg, but if we're dealing with D, we'd have to be working with A. So this hypotenuse goes with this leg, as this hypotenuse goes with this leg, because then we're looking at the smaller triangle. All right? All right, 10 and 11, we're going to have to actually use that. So take a step back and think about what you have and what you can use to figure that out. So for like number 10, I'm going to solve for x and y. I have to do two different things. So let's say the whole long hypotenuse, so 60, is to, supposed to be 20 then, 20 as, I don't know, I have to use y there. Oops. 60 is to the one leg of that triangle, y as y, so that's the hypotenuse of the small leg, is to 20. And when you solve that, you'd have y squared equals 60 times 20, which would be 1200. You take the square root of 1200. I don't know if that works out nicely, but 1200 and the square root of that, 34.6. We'll round it to 34.6. So that's about what y would be. And again, you can look at it and it makes sense. It looks about that size if you were to compare the parts. Um, we'll do x, then we have to figure out x. Let's use the other one. Let's say, if we're using the altitudes, let's say, um, 40, the longer part of the hypotenuse is to x, as x is to the shorter part of the hypotenuse. So we'd have x squared, when you do cross multiplying, would be equal to 800. Let's see if the square root of 800 works out. I don't think it will. Oops, 800. 28.3. If you look at it, that does seem to make sense again. Alright, I'm going to have you do number 11 on your own. And that's actually the last problem we're going to do. So do that now on your own, please. So I just did those for you. Hopefully you can check them out, see how I did the work. Unfortunately, they're not going to work out to be perfect whole numbers, but that is how we get both the x and the y. So if you have questions on that, let me know next time. Otherwise, try to answer the error analysis and the closing questions, and we'll talk to you next time.